So welcome to this month's San Francisco MySQL meetup. I'm glad you guys made it out, even though there was a threat of rain. Tonight our sponsors are just Percona for food, like they do every month, pretty much, and Lithium for this space. They also pay for Mike's time, and Zendesk for allowing our speaker to come and speak to us tonight. It was a little bit on short notice, it felt like to me, but Morgan.
Okay. What do you think of? For me, I thought of a moment walking down the street where I was preparing this little, stupid thought exercise. I was wondering how many people would show up, right? I was at my hairdresser's, right? It was just this series of moments, and I could see them as still frames, right? I could see me and myself in the mirror. I could see the rain coming down on the street. Now, I wonder if anyone actually saw this as I think time really is, which is a series of mutations, right? Because I think when we think about time, right, when we think about the past especially, we think about a series of still frames where you can stop time. And so we build up these constructs into our data systems. Like this is what MySQL is, right? When you query the database, you're not querying a living organism. What it's doing is, with MVCC, it's freezing time at the moment that you run that select, right? And you're viewing the past, but you're able to view the past consistently, right? That's the power of this kind of data store as MRDBMS, is that you can see all of the world cohesively as one, and you can take little bits. How many people live in that building, right? How many people are brown-haired in that building, right? You can take all those bits and kind of like coagulate them together into one sort of meaningful thing at that point in time. But I suspect that the world is actually more like this. That there's no real now. That there's no 5 minutes ago. It's just this series of mutations, of things that transition states. Okay? And then if you look at it, you can never really freeze time. I'm Ben Oshoff. I lead a small 4-engineer team at Zendesk, doing lots of back-end stuff. I've been doing the web for about 15 years. I've done specialty in MySQL and products of scale for 10 years. Before Zendesk, I helped build Highlight, which was one of the first big Facebook applications. We had to scale from nothing to 2 million very quickly, and then 2 million to 10 million. So I sort of assigned myself the back end because nobody else seemed to want to do it, or they were scared. Anyway, but mostly as an engineer, I'm trying to ship products, get some stuff done. And I wanted to talk to you today about Maxwell's daemon. Maxwell's daemon is a side effect, a nice product that came out of the last couple projects that I was working on. And it's a change data capture system for MySQL. And a change data capture system takes the series of still frames, right, that you see in MySQL and translates them into a series of mutations, a series of log events, basically. I've been working on about 9 months now, Maxwell. And the premise of Maxwell is to help you look at your data as it lives, not as it, as it dies, right? Every time you look at your database, every time you query your database, every time you join your database, you're looking at a corpse, right? And so Maxwell, a little bit pretentiously, is going to try to help you look at it as a living entity. Simply though, you put data in, and you get events out. And this is actually a live capture. Well, it's not a live capture. What are you talking about? This is a capture, a screen cap of some of Zendesk's Maxwell stream. So every single event that happens on your database is captured by Maxwell as a JSON stream. Okay, we'll get a little bit into the history of Maxwell. Oh, also, Aaron said you guys stop the speaker at any time for questions. I'm fine with that. If anybody has any questions, if there's anything not clear, please let me clear it up because I don't want to be just like blabbing and not being understood. Okay, but Zendesk architecture looks like this, crudely enough. MySQL is our primary store. We also have React and Cassandra and your host of alternative stores, but at the core is a lot of MySQL data. We run them in 3-node clusters, and clusters makes up a pod that are serviced by the requisite application servers and work queues. Very standard stuff. You've seen all this before. And then the pod, there's multiple pods. We have 10 or 11 pods. And a couple of years ago, we were looking for a way to balance data between pods. We had one pod that was very, very expensive to run. It was a managed hosting pod, a legacy one. That was good. The legacy hosting was good, but they were charging us an exorbitant amount per Fusion IO device. So we were looking around for solutions on how to basically get out of that pod. We had a solution, I'm sure some of you have seen this before, where there's a script that shuts down some subset of the data, quiesces it against writes, and then throws everything over across the internet, and then brings it back up. There's also the option to just sort of, chain replication slaves over the internet and all that. But the problem was handed to me, and I said, okay, well, maybe we can get a product where, on an ongoing basis, we can, transition our customers' data around the internet with no downtime. And so I built this project called Exodus, still a couple of years ago, whose goal is to move one of our customers. This verbiage is always confusing. Moving one of our customers means moving one of our help desks. So we're a SaaS company, we host many help desks. And so to say we move a customer or an account means we move a subset of the data in a cluster to a different physical location. Anyway. So running Exodus, the heart of it is the MySQL mover process. I'm not sure if you can really see that, but there's a timeline here, and the first thing we do is we dump the data, right, and then we're going to, okay, this is like the design phase of Exodus, right? We dump the data, and then we capture a binlog position, right, transfer all the data over the internet, and then at some point, we're done with the snapshot transfer, and then we start sweeping deltas accumulated in the binlog over on top of the other cluster. And so at a certain point, all the deltas are swept, the snapshot is there on the other side. We quiesce the account for maybe 10 or 15 seconds to get all of the writes finished on the other side. And then we cut a pointer over and there you go. So that's the design, but the reality is that it was a little bit more complicated than that, right? Just capturing the deltas, I thought, okay, well, you can capture, row-based replication. You can capture that as a stream and maybe transform that back into SQL or transfer it as, JSON or something. But it's not quite like that. MySQL's binlogs. I don't know how many of you have experience with row-based replication, but if you MySQL binlog one of these files, it comes back without a lot of the requisite data that you need to actually transform it back into SQL. Ints aren't assigned, characters have no encoding, right? So the replication slave is, and also more importantly, there's no column names, right? There's just 1 through 10. So the replication slave has enough information to apply that update out of the stream, but we couldn't quite use it just as it is. So we needed to get some help. So we said, okay, we'll go to T0, and we'll capture the whole schema, right? We'll capture the schema as it stands, and then all throughout the process of transferring this data over the internet, we'll be checking the schema. Did it stay consistent, right? Because we have, well, note that we're transferring these between different clusters, so you have to make sure that the schema in cluster A is cluster B is also the same, because when alters happen, those happen at any sort of given moment, right? Those can't happen synchronously. So you have to check your schema updates, and basically we said if any schema change happens between T0 and TY, we'll just abort the process, we'll go again. And so that was kind of ugly. We put a little HTTP server on the MySQL nodes. We said, okay, give us from this time to that time. Okay, now give us from that time to that time. And we just incrementally basically paginate through the bin logs, sweeping deltas as we went over to the remote side. But this approach worked. It was very pragmatic. We managed to transfer our terabytes of customer data out of our legacy pod and get to the new pod in a couple of months, all told, with a lot of fixes and yada yada yada. But importantly for this talk, it sort of got me down the got me thinking of the world of deltas and what possibilities that opens up to look at the world of deltas. So I'll take a hard right turn here and talk about. It was just the next project that I had queued up for myself, kind of coincidentally, was Zendesk views, right? Solving a scaling problem of Zendesk. Views are our main workflow tool, so they're just lists of tickets that a customer defined lists of tickets. And they look like this. This is not what they look like. They look like lists of tickets, but this is how you administer a Zendesk view. You set a condition and operator and value. And this is clearly just a SQL builder as designed, and that's what it is under the hood. But some things to note is that there's contextual conditions. Ticket group is current users group, so there's sort of dynamic conditions. There's ticket description contains one of the following worlds. That's a free text condition, right? So it compiles down to a like clause. And then there's a sort of an and of ors here down at the bottom, where meet any of the following conditions. Mostly, our scale story for views is pretty good, right? It's been sort of beaten into submission over, I would say, 4 or 5 years of Zendesk, right? Of hosting big customers and falling over and getting the indexes right and getting all the caching right and that sort of engineering that you do where you just sort of beat it with a very, very blunt hammer until it scales, right? Until it stops having problems where at least it tips you over. But even so, it's, I don't know, it tends to blow up every once in a while. It's a feature that has trouble scaling. We have certain customers that have a working set of, I would say, about 500,000 tickets. So that's basically tickets go through a lifetime in Zendesk. They go from new to open to solved to closed. When they're closed, we can stop looking at them for most cases. But in the working set before they're solved, they're available for these kind of workflow items. And so we have a customer that does about 500,000 unsolved. They have maybe 60 million or so overall. And they use a tag condition as their main workflow delineation. And it's just really hard to optimize, right? So I was a little bit prescient on this at the beginning of the year, and I knew we had to solve this. And I've been thinking about this, and so the first idea I had was to do view caches, just sort of based from the front end. So this is, you'll recognize this pattern mostly as a materialized view, but done from the application node. Right, so ticket update comes in, hits the main database, and as a side process, right, sort of a side chain process, it'll say, okay, I have this really expensive SQL that I can't really, operate in runtime in a frozen world environment. So I'm going to go check to see if this ticket matches. I'm going to push it into this view cache or remove it from this view cache, right? And then when we go and actually check the views, if we have a cache, okay, great, we can just hit the view cache. I prototyped this just using it right in the application, right alongside the ticket update. And it kind of worked, but it was really, really ugly from a design perspective. And when I went to go actually solve this problem, I still had this notion of view caches, but I wanted to do it a little bit more elegantly. And so I had this component in mind, which was the fire hose, right? You've seen Twitter's fire hose, where they just let you suck on an HTTP stream of every incoming tweet. And I said, okay, well, we should have that for our databases, right? We should have that for our ticket updates. We should have a series of mutation events that come in, and then we can latch some kind of stream processor onto the back of that data fire hose, and build our caches from there. And then it's completely decoupled from the application, and also you never risk missing an update, right? That's the main awesome abstraction that a stream or a CDC system gives you. It gives you a linear list of updates that you just walk through, right? And as long as your client is good with its pointers about where it is in that list, you're not going to miss an update. Which you might if you just said the application, if you're here and the application has to basically double write everything, right? Which is something that a lot of people do when they're building streams and bus kind of systems. They have the application double write, right? On commit, they will write a row into some kind of bus for other services, for other components of their system to notify, right? But it's very hard to get that error free because you have two pieces of data now to synchronize, right? You have your main mutation to the database, and you also have your stream event, right? So if the event itself is the primary thing, that's a fine thing. Your app node should write it, but change data capture is kind of more powerful for mutations to the main database. And so this is sort of what the whole system looks like that we've built right now around view caches. Right? So ticket update comes in, it comes into MySQL, it comes out into the bin log. Maxwell, the fire hose, processes the bin log and pushes it out to an event bus. In our case, this is Kafka, right? And then we have a match engine that goes and reads the Kafka bus in series and says, okay, I can maintain my view caches based on, I'm reading this stream, I'm going to evaluate the rule in runtime, basically. And we have real-time processing updates. Now, all of this, the event bus, match engine, cache, this is sort of the last 3 months of my team's work. So we've basically got an alpha product that we still need to prove. But Maxwell is complete and basically ready for the world, so I wanted to get into that a little bit. This is what it looks like if it was drawn by a 5-year-old. So data comes in from MySQL, goes out the bin log. We keep a copy of the schema that's on the side from the bin log. And then when a new bin log event comes in, we merge it with the stored schema, convert all the fields to JSON, and throw that out into Kafka. So you get SQL in and JSON. It's a very simplified model, but it's kind of interesting. And I'm going to get into what you can do with this because this looks like a child could do this, right? But just quickly, the dates are stored as just MySQL dates because there's no time zone information there. And then if you have a block column, we output it as base 64, right? We give you a timestamp that the transaction that also a transaction ID because we output one Kafka message or new line separated event per row that's updated. Not MySQL's binlogs events come in big packages of rows. So we separate that out into row by row just for ease of processing and uniformity. But then it means we also put a transaction ID on each row so that you can recorrelate them back into a big batch if you want to do that later. And then here's the sort of neat thing. So when you update this row, we've put in this row with text hello, that's 1.3. Yes. How do we capture schemas changes? Yeah, so we have a SQL parser, basically. We've written an Antler-based SQL parser. Basically, when Maxwell first starts up, it goes and it just does a show create table, or it uses the information schema database. It captures everything as it stands. And then as it reads the stream, it actually parses alter table foo, set add column this, remove column that. Which has been, there was no other great option for doing it because that's how MySQL presents schema changes into the replication log, right? So at a certain point in the log, in order to sync the schema with the binlog event, you basically have to parse the SQL. There is another solution involving kind of like just sort of shoving it at the side of MySQL server and letting it parse the SQL and then rereading the schema, but I didn't think of that at the time. So anyway, we have a full DDL parser in Maxwell that can basically act as a fully qualified replicating stick. It's been the biggest source of bugs, that's for sure, because I'm trying to match MySQL's, like 15 years of MySQL parsing. But right now, it's been in a place where it's been stably in Zendesk's production for a couple of months, and then as new open source people come, they find new places where the SQL parser is mismatched, but we fix those. You insert a row, you get out JSON, you update a row, right? And since this is row-based replication, you get the full row back, right? This is really powerful. Same thing that you can do with row-based replication, where you always have the current image of the row that you're working on, no matter whether it's an update or what. I have a feature that you need to do. I haven't needed it yet, so I haven't built it yet, but updates in MySQL's binlogs have the old row image too. And so I should be able to provide, well, here's the data as it stands, and here's also what actually changed in this row. So that should be useful for working out kind of delta events, like how many people changed from option A to option B, right? Or in the case of view caches, was the ticket previously in a cache and then did it leave, right? Stuff like that. So implementation-wise, it's got an open replicator fork at the core of it. Google has a replication library called Open Replicator. It's really good, although they abandoned it, so I've taken it on, added some features to it. It acts as a full MySQL slave like I was just talking about, so it's got the DDL parser, and then it can also parse all the replication events and all that stuff. And it has no external dependencies. Right? That's this third point here, is that it stores state position and everything. It stores its own schema inside of MySQL itself. So it's got a very low operational overhead, right? You don't have to set up, you'll have to set up Kafka if you want to use it that way, because that's the way it probably should be used, but it can be used just as like standard out. But other than that, it's just everything is MySQL, no external data stores, none of that. I just like things with very low operational overhead, developers friendly. So then conceptually, like this I want to talk about like, yes. You can, yeah, the guarantee that we make is that you won't lose data. You might duplicate data, right? And so, that's right, yeah. Right. And that's, I mean, when you're talking about queues and buses, right, like you have to pick one of those, right? You can't, like, once and exactly once is a fictional myth that you cannot do. So, at least once delivery is what we guarantee to Kafka. I mean, there's some tricks that we could play to do very good things. Like if we wanted to read the last positions of the Kafka buses, right? We could say, okay, well, I know I can intuit that I'm actually there in the log because we snapshot our replication position in MySQL once a second, right? So we flush that once a second to avoid just writing one event per row entry that we get down. So
Would it matter? Practical application system. It doesn't matter.
I mean, it depends on what kind of system you're building, right? Your counters might be off if you're building bank systems or something, right? Like I can see a scenario where if you're trying to roll up very, very exact bits of data based on things, you would have to like maybe keep a small buffer window where you say, oh, I just saw this insert of this exact same update, right? Maybe the exact same transaction ID. Actually, I think that once is totally impossible for Maxwell now that I'm thinking about it, but the level of guarantees is good enough for my uses. I think it's probably okay for most of what you want to do with these stream systems, right? Just sort of what I'm getting into. Especially when a lot of what you're doing is kind of like, take this whole row image that's already there and then just slam it into this other system, right? Or basically, streams are very good at idempotent kind of changes, right? And Maxwell gives you idempotency. So yeah, so what do you do with this? What do you do with this stuff? Like, presumably you've gone through the motions and you've pushed out your MySQL updates as a stream of captures, right? Like, what do you go and do with it at that point? And ETL is one of the big answers. ETL gets very, very easy at this kind of stage, right? I don't know, like, how many of you have systems where, you have a search indexer, and it basically has a process whereby it grabs a corpus of data, right, at a certain point in time, and it's booting up the search index, right? Okay, go create a new search index. Okay, go grab all 200 million rows from the database, go slam those into Solr or Elasticsearch or whatever, right? And then as a tailing process, we'll pull the database from new rows. That's a very common thing, right? Or maybe the application will fire a little side, a little work entry into the side bus that says go re-index these things with that zero code. So like at Zendesk currently we do the polling method where every table that we want to index has a timestamp, right? A create ad or an update ad or an actual MySQL generated timestamp, kind of timestamp. And we'll go and say, okay, my pointer is here in time and give me the last 20 seconds, right? And I'm going to change data capture system like Maxwell makes that kind of process look a lot safer, right? Because what you have is, instead of having a timestamp that you go back in time and you have to make sure all your tables look the same, right? What you have is a series of mutations. So you say, okay, all the mutations came in and this ticket changed, great, go reindex this, right? This user changed, go reindex this. Likewise, data analytics or offline processing is great for that. So one of the first production consumer of Maxwell, they beat me to it. The system that I'm doing is not in production yet, but these guys are building a data analytics thing where they look at a ticket and they do some sort of sentiment analysis and they say, okay, what's the percentage of this ticket pleasing the customer? Basically, what's the percentage that the user is pissed off, right? And so they had a solution previously where when a ticket update came in, it fired off an event into a Kafka bus, and then it would go out and refetch the data, right? And then with Maxwell, right, they have a much more reliable bus, right? It's just a baked-in bus to your infrastructure where you can listen to mutations like that and say, okay, new ticket came in, I need to go like refetch the ticket and do sentiment analysis, right? And if they're smart about it, they can also say, okay, well, the data is actually there in hand, and so when I go to analyze the sentiment of this ticket, right, I can just look at the bus as it's coming out. And then the view cache that we talked about. But what I'm kind of wallpapering over, what I'm kind of like faking you out on, is that some of these problems are actually hard with a change data capture system too, right? So the guys who are doing the ticket satisfaction prediction, currently they can't just use Maxwell. They go and they refetch the data because of this thing about denormalization in the stream, right? So for a Zendesk ticket is a single table, but it's also like 5 or 6, side tables, right? So you have the ticket, you have the comments, you have some custom fields, whatever. Like, compositely, there's maybe like 50 or 5 or 10 tables, let's say, that make up like what it actually needs to be as in this ticket. And so if you think about like the update stream, right, at any given time, as you see the update to that ticket, you may only see a little bit of that update, right? You may see that its custom field updated, or that it got a new comment, but the main ticket row didn't change, right? Or just the ticket row didn't change, but there was no new comments, so then you're left with this kind of disconnected state where you only have little bits and parts of the thing. And so like the people who are working in this space of stream processing, like the Apache Samza guys, I think the Spark guys, but maybe not, they're a lot smarter than I am when I'm thinking about this kind of stuff. And like Samza puts a whole like key value store into your stream processor just for the purpose of you doing this kind of like denormalization, so that like when a widget that's green comes in, you say, okay, I just stashed that away. And then when a user gets associated to a widget, you have stashed that away. And then, basically you end up building these projections, these like sort of micro projections of your data at any given time in the update stream, right? And so this is just like, this is kind of a cumbersome bit about stream processing. And it's hard, and it's not easily tractable to answer questions like how many users have a green widget installed. Now, answering questions like how many users have widget 1, 2, 3 installed, like stream processing systems are great like that. They're widely parallelizable, right? You can talk about like 50 workers reading from a stream all at once, right? A parallelized stream all at once, and running up their counts and then rolling up their counts periodically into some sort of central data store. Right? That's a great usage. But once you start trying to correlate data, it gets really, really tricky. So I want to work on some of this kind of stuff. Basically, as I do more on like my view caching system, I think I'm going to need a denormalized stream of tickets, right, with all of its subsequent fields. And so hopefully I will be able to work on some kind of like denormalization project. But anyway, I guess the last thing I wanted to talk about having a CDC system in Maxwell and all that stuff is that problems that seem kind of hard become easy, right? Just like in denormalization, things become very hard, but like other things become easy. So cache expiry or having like a memcache is super easy, right? You have the full row of the image in place there, and it's really easy to just slam that into a memcache or expire all the caches that deal with that primary key, whatever you want to do, right? Whereas that can be tricky and error prone. You're dealing with updates happening from like various parts of your application. You have to make sure that you don't miss an update, right? Stuff like that. So cache expiry becomes super easy. Metrics become like really, really nice in like a CDC stream system. Like I built like a very like trivial little Datadog dashboard off the Maxwell stream, just showing like our most active tables and like what table is the most inserted, what table is the most updated, what table is the most deleted, right? Which I was like, well, that seems like something that I should know, but it was kind of like hard to get out, and like I was thinking, do I have to instrument the whole application? So Maxwell helped me do that really easily. And then of course like alternative storage, and that's the whole ETL world again, just becomes so super easy in that kind of thing. If you're looking at like taking from your primary storage and pushing off into a secondary store for whatever reason, CDC systems and Maxwell will help you there. So this is summing up. Yeah, open source, Apache 2, 0.9 quality. It's in production at Zendesk, amongst various clusters. Still working about the bugs, which is why it's, maybe it's 0.8 if you're going to be totally honest, but it's actively under development, and we're going to add new features. Thanks for coming out. Anything else? Tungsten. Why not using the tungsten? Yeah. That was one of the first products that we looked at when we captured it. When we looked at doing Exodus, like long ago. I think the thing about tungsten was I didn't like how it wanted to take over your replication stream. I know you can do like the single slave node, but for our purposes, like we wanted to get it like basically back in the Exodus days when we were doing like row-based replication. We're like, okay, I want to get row-based replication back into SQL. That was actually my thing. And it was just like trying to write one of those plugins and like figure that stuff out. It's just like I didn't get it. I didn't understand what they were going for, their metaphors, right? And like that can be a big piece to developers. Like what is the primary like cause here? I also wanted a system back then. Tungsten wouldn't be actually a bad system for Maxwell, I'll give you that. But when I first started looking at this stuff, I wanted to be able to like play it from a given time, right? I wanted to say, give me it from back here and go to here. Tungsten didn't have that functionality. Just row-based. We do minimal processing on statement-based, but it's impossible to actually transfer statement-based into our format, right? Like when you say update foo set A equals 2, right? Like I can do a full SQL parse and tell you what the value of A is in that context, but then it's divorced from what the normal Maxwell format would look like, right? So you just get the value A2 in your row. You wouldn't get the full row. So it's only row based. I'm not sure I understand the question. Can you be a little more clear? As far as I know, it shouldn't matter at all. I don't think it. Maxwell just feeds as though it were a replica. I'd actually have to look at that because I don't know what the protocol is for a replica hacking that it actually applied a transaction, or if it's just that it if it read a transaction. The only thing I can think of is Maxwell might actually interfere with that world, right? And if it's acting as replica slave, your MySQL master might be fooled into thinking, I passed this transaction to Maxwell, right? Like,
At the same time, we're not doing that.
yeah,
And we're doing anything on the slave.
on the master. Yeah.
Does it add any
Only that which, it depends on the size of your schema. It can add a little bit of load because it stores the schema back in the master, right? And like for us, we have, I don't know, we have like 100 tables in each shard, which is a logical database on disk, and then there's 10 of those logical databases per cluster node, and so like you end up with this like 30,000 rows per schema, and then each time the schema changes, it just stores this whole new snapshot of that. So that can put a little bit of pressure, but with smaller schemas, no, and then it just acts as a replication slave, right? That's its normal running state is a another slave in your system, right? No more than that. Well, and a single update per second, but I don't think it was it.
Even not being on the slave.
What now?
And even not being on the slave.
Just that it needs a write connection and it needs to track its position within the master log, right? There's a bit about failover, master failover, that haven't really worked out yet. Maybe I can kick it down the road until like MySQL 5.7
That's
becomes
the
like,
next question,
yeah. Basically, it does have some minimal MySQL master change detection. If it detects that it's on a new server ID, so okay. Let me back up. The way I have Maxwell running in production right now is I have n nodes behind a distributed lock, and they're all trying to get, when they boot up, they say, okay, who's the master in this cluster of 3, right? This is all a script that's outside of Maxwell. Maxwell is just pointed at one server, right? They all boot up in a cluster of 3, and then they find the actual master, and then they go work on that, right? Now, when the master is demoted, they see that it's read-only, they crash, right? And a new process comes up, finds the new master, and starts going. But basically, there's no correlation currently between the old master and the new master, right? Because we're not using GTIDs, and that's a hard problem. So it just says, okay, well, get rid of all of that old schema. I'm just going to start wherever you are. I may try to solve that by like going back and correlating it to where it last left off in the old master. But there's one place where we don't guarantee that your data is, that you never lose an update, is on master promotion, master change. I think I need to solve this problem before global transaction ID support, but it's tricky, and that's just a lot of time. Cool. Any other questions?
You actually expose the schema change in the process, or is it just a
I don't, but it's trivial to do, if I wanted to. I'm trying to figure out what like benefit it would be, but like, I don't know, it could be neat to tell like Streamless, there's this new column on this table in a very structured way, and it's got this type. If there was a use case for it, it wouldn't be much work, because I have it there, it's parsed, it's put into a fairly, it's parsed into an object basically, a schema alter object. So it's not hard to say this is a JSON object that represents adding a column to this table, right, in this database. So, the answer is no, but if anyone requested the feature, I would probably do it, because it's not hard. I'm the primary engineer, I'll say. I have a team of 4, and 2 of the other guys have good familiarity with the code base, but I'm sort of like the one that wrote it, so I tend to be the one that works on it. We do like code reviews and +1, so every bit of Maxwell code that I write is seen by 2 other people, so there's at least that plus factor. But it's mostly